So let me turn them all on. So tell me what do you think you're going to be able to easily identify which one is which? Now they're cheating a little bit because they're identified by color.
Except for the Gaussian and the square one. Those are the same black.
Okay.
But
do you think that you're going to be able to identify them by shape when it's all zoomed out like this, or any way?
I think it might be kind of hard when it's zoomed out, but right at the beginning you'll be able to tell.
You should be able to, but if there's a lot of long jumps with the Gaussian one, you could sort of easily identify that with a long jump.
Oh, okay. So if there were some long jumps, maybe you could identify that.
Or,
hold on a second. There we go.
So yeah, the Gaussian one jumps significantly more than the rest of them.
So the Gaussian one's the gray one?
Yeah. Mm-hmm. The square and triangle ones seem the most
spread out. Now
actually, the triangle one's more spread out than I thought it would be. The square and the ring are kind of localized, and the triangle one can just jump all the way down here. And the Gaussian one's the biggest cluster.
Okay. What do you think?
So the triangle one, it didn't look like the one we ran in the beginning because this time it's sort of like bounced out and it's sort of forming a cluster over here.
Uh-huh.
And I think in the beginning it was sort of staying localized. And the ones that are the ring one, is you can see there's just a big cluster around here and it's not really moving. The square one is now moved over here, and then the Gaussian one also moved a lot all the way over here.
Yeah, so what do you think? You think if I asked you which one the red one was, you would know?
Probably not. I mean, you can kind of see like these angles here,
yeah, I think,
but you can kind of see a similar angle up in the Gaussian one.
And I think the easiest one to identify would be the square one, because you can sort of see how it's traveling. It's sort of stuck to the axes.
You can see the right angles in the square one.
Alright, so without zooming in though, so if you can't quite see the angles every time, what do you think?
I think probably not. I think that if you gave these four to a person, and it would be kind of hard to tell which one was which.
Does that surprise you?
It kind of does, because we're doing pretty different things for each one of them. Like here we've got 3 points, here we've got 4 points, maybe these look similar, but here we've got the full 360 degrees. So that should look different, and then here we're not even jumping the same length every time.
Yeah.
So you'd think that looks very different.
But really, I mean, this one, there's a lot of similarity between the triangle one and the Gaussian one.
Yeah.
They almost kind of look like mirror images.
Oh yeah, nice.
And the square and ring are localized.
Yeah, it's cool. So it's actually what this is showing is some sort of micro properties of randomness. So we can see when we zoom in really far, we can tell them apart because this one has different jump sizes. This one's sort of a continuous ring. This one only goes in specific directions, and this one only goes in specific directions. So when we look at the micro properties, we can tell them apart. When we zoom out and look at what's called what?
Macro
properties. They're very hard to tell apart.
Yeah.
And that relates to something up here called the central limit theorem, which is something we've looked at before. So it's cool. It's a neat way to see randomness. So it doesn't, surprisingly, if you just randomly walk around in some paths determined by these different outcomes, all your paths kind of look the same.
Yeah.
It's a surprise.
Yeah.
Cool. It's a fun program. All right, good job, guys.